So we're looking at the limit as x is going to infinity or negative infinity. That's going to help us find horizontal asymptotes. So for instance, if we have the limit as x is going to infinity of some function f of x, and this is equal to a value L, then or we can have the limit as x is approaching negative infinity, so the other end behavior or graph of f of x. Maybe this is also approaching L. So let's say we had our y value L here. What this is saying is x is going to positive infinity. Our graph is going to start hugging this horizontal line y equals L. Might look like something like this. Or as x is coming in and going to negative infinity, you also could be hugging this graph, y equals L. Notice in this case, so those are horizontal asymptotes. We talked about, if you're looking at a rational function, that you had to look at the degree of the numerator and the degree of the denominator to determine if it had a horizontal asymptote. And if the degrees were the same, then it was y equals the leading coefficient of the numerator over the leading coefficient of the denominator. If we had the denominator greater, then it was the x-axis, y equals 0. The numerator, degree of the numerator was larger, there was none. So that was back in the notes from before, but just kind of recalling really quickly. And so also we talked about vertical asymptotes. So in this case, this is occurring where the value, the limit as x is approaching some value. In this case, this is the x-axis or y-axis. So as x is approaching 0 on the left of f of x, notice that this graph is shooting up to positive infinity. And then if we look at the limit as x is approaching 0 on our graph, on the right of f of x, so as we get closer and closer to x equals 0 on the right of the graph shoots downwards and then is going to negative infinity. So we also talked about how to find vertical asymptotes and where they occur. If you were looking at it, a rational function, there was values which set the denominator equal 0, but not also the numerator. If it set both of them equal to 0, that meant that they factored and that you could simplify by canceling like factors and figure out what the limit is. That was an open hole at that point if they caused both the numerator and denominator equal 0. So let me just pull out an example. Okay. Find the limits. Just want to use this to graph. Okay, so let's graph the rational function, include the graph, the equation, and the asymptotes, and dominant terms is what it's telling us to do. Okay, so if we had, let's say, f of x is equal to 2x all over x plus 1. Okay, so right away I can tell that I have a vertical asymptote where x plus 1 is 0, and so x plus 1 can't be 0. It's undefined when x is negative 1. Negative 1 doesn't set my numerator equals 0, so I have a vertical asymptote on the line x equals negative 1. So horizontal asymptote, that occurs when both the numerator and the denominator are the same degree, or if the degree of the denominator is larger. If I look at the degree of the numerator, the exponent of this x is 1. Same thing in the denominator. So the degree of x plus 1 is also 1. They have the same degree. So I have a horizontal asymptote at the leading coefficient of the numerator, which is 2 in this case, all over the leading coefficient of the denominator. Well, no number in front of x is 1. And so we have a horizontal asymptote at y equals 2. So knowing where those asymptotes are, and maybe a couple of other important points, your x-intercept and your y-intercept, are very helpful in graphing these functions. So we're going to find and use a lot of tools of calculus to help us graph things. For instance, where graphs are increasing and decreasing, how to find maximum points or minimum points of graphs where you're like at the top of a peak or coming down at the bottom of a valley. But so right now we're graphing these rational functions and using limits to help us. And so let's draw our vertical asymptote at x equals -1. And so I'm just going to denote that by a dotted line. And then we also have a horizontal asymptote at y equals 2. So I have a horizontal line at y equals 2. I can figure out a couple more points if I wanted to. So let's figure out what our y-intercept is, if there is any. So if we looked at f of, well, y-intercept occurs when x is 0. So plug in 0 wherever you see an x in your function. We have 2 times 0 in our numerator, all over 0 plus 1, gives us 0 over 1, which is 0. So it looks like I have a y-intercept at the point 0, 0, or at the origin. So x-intercept, that's going to occur values which set basically when my numerator is equal to 0. X-intercept, we set y equal to 0 and solve for x. But when I do that, I get 0 equals this rational function, 2x all over x plus 1. And if I cleared my fraction here and multiplied both sides by my denominator, x plus 1, basically I have 0 times my denominator, which is 0. And x plus 1s would cancel, so I'm really only looking at, or only worried about, when is that numerator equal to 0? So we're looking at when is 0 equal to 2x. Well, divide by 2, that's when x is 0. So I know it's not going to cross the x-axis anymore. I know that it has to be hugging, and we can look at that. Let's look at the limit as x is going to positive infinity. And I'm going to give you some tools here to help us. So if we were looking at limit as x is going to positive infinity, notice that this right here, we're going to have 2 times infinity. So that's growing really large, right? And it's still going to infinity even though I'm multiplying it by 2. And I'm also having this infinity plus 1. So they're really growing really large, pretty much as fast as one another. And so this is technically infinity over infinity. So when we got 0 over 0 before, that was an indeterminate form. That didn't tell us anything, and we didn't get anything from that limit. And we had to go back and we had to manipulate the function that we were using to help us something to fall out so that we knew what was happening. And so this is an indeterminate form here. So the way to manipulate it when this is happening is let's look at the degree of the numerator and the degree of the denominator. Basically, we're going to multiply this rational function by a fancy 1 to manipulate it so it falls out. You're going to look at the highest degree. So basically the term here with the highest degree is just x, or 2x. And what we want to do is we want to divide both the numerator and the denominator by that value, in our case by x. So we're going to multiply this by a fancy 1. So we're going to look at the limit as x is going to infinity. 2x all over x plus 1. And I'm going to multiply the numerator by 1 over x. And I'm going to multiply the denominator by 1 over x. So when we do that, if it helps you think of this 2x over 1, and you can think of this x plus 1 over 1, if it helps you. So basically here we have 2x all times 1 over x. Those x's are going to cancel. And all we would be left with in our numerator is 2 times 1, which is 2. All over. Well, I need to distribute this to each piece in here. So if I do that, this would give me 1 over x. I'm sorry, not 1 over x. It gives me x over x, which ends up being 1. Plus, and then distributing it to this 1, I have 1 over x. Let me just bring down my limit, because I haven't taken it yet. And then let me simplify a little bit before I take the limit. Well, this x over x, right? This is the same thing, it has just 1. So right now we're looking at the limit as x is going to infinity of this 2 all over 1 plus 1 over x. So if we go in here and we plug in infinity and think about what's happening as those values, as x is getting really, really large, we can figure out what this limit is. And so here we have 2. Remember, a limit of a constant is just, it's a value, that constant 2. The limit of the denominator, so that would be the limit as x approaches infinity of just 1, which is a constant, which is this 1, plus 1 over, so x is going to infinity here, of infinity. So we talked about yesterday that 1 over x as the limit as x is going to infinity, that is going towards 0. And see, we're going to use that a lot to help us manipulate these to fall out. So some constant over infinity, that's going to always go to 0. And so this here then can tell me that this is equal to 2 over 1, which is 2. Which makes sense if we're looking at our graph and knowing that that horizontal asymptote was going to occur at 2. This graph is going to hug this line as x goes to positive infinity. So let's look at the limit as x is approaching -1 on the left-hand side. So technically, this graph here, it could either come dip back up here and hug this asymptote, or it can come down here and hug the asymptote here. So we want to know, is that value, is x approaching -1 on the left going to positive or negative infinity? And is the limit as x approaching -1 on the right going to positive or negative infinity? So let's look at those limits real quick. And so limit as x is approaching -1, I'm looking at the right-hand side right now, of f of x. So f of x, that was 2x all over x plus 1. Okay, so it's undefined at -1, but if I'm plugging in a negative number that is close to -1 on the left, that means that number is bigger than -1. So maybe -0.9 or -0.999. But when I plug that in, we just want to think about, is that rational function in the end when I plug in this number going to become positive or negative? And so when I plug in -0.9 into the numerator, 2 times that -0.9 is a negative. All over, okay, so if I plug in -0.9 into the denominator, a -0.9 plus 1 is positive. And so this will be positive in the denominator. And so negative over a positive is negative. So this shoots down to negative infinity. So let's look at it coming into the right-hand side.
Are you writing something right now?
I am.
Okay, it's kind of just stuck on like a couple minutes ago. It's stuck right there.
Okay. Did you hear me at least
Yeah,
talking?
yeah.
Okay. Is it coming up into the screen?
No.
No.
Looks about the same.
Okay, let me pause the video. Okay, so everything was just fine. Technical difficulties were inverted. This is where I was writing up here instead of down below. And we were just looking at the limit as x was approaching this -1 on the left, and we saw that this was coming downwards. Because when I plugged in a negative number into this, and a negative number that was bigger than, because it's coming on the right of -1, so -0.9 works. So 2 times a -0.9 in the numerator would be negative. And then a -0.9 plus 1, or anything to the right of this -1, is always going to be positive down here. And that's where we got this positive. And I know when I divide a negative by a positive, it's negative. So that meant that this graph was going to -infinity on the right. Just make sure that that's no emergency, which it's not. You never know these days. So let's look at, let me change the color for you guys. Let's look at the limit as x is approaching -1 on the right-hand side. Not the right-hand side, I'm at the other right, which is your left. And so we have 2x all over x plus 1. And so again, let's just kind of think about, are we going to get a positive or a negative number back in the denominator and the numerator? And so if I'm plugging in a negative number coming in on the left-hand side, so that's like -0.1, -0.01, -0.001, and I multiply it by 2 in this numerator, that's still always going to be negative. But when I plug in a number down in this denominator and it's negative, and it's going to be bigger than, smaller than -1. So -0.1 plus 1, that's negative. -0.01 plus 1 is still negative. Those numbers coming in on the left-hand side of -1 is going to make the denominator negative. And so when I have a negative divided by a negative, I know that that's a positive number. And so this is actually going to be going to positive infinity as x is approaching -1 on the right-hand side. We have something like this. So let's just look at the limit as x is approaching -infinity and show that we would also get back 2 in here, even though that we already saw that that's where a horizontal asymptote was going to be. We can kind of use the same reasoning as we did below here. Maybe I should have done that the first time. But if we had plugged in infinity or -infinity into that function, 2x all over x plus 1, we're going to get 2 times -infinity. 2 times -infinity, well, that's -infinity, all over -infinity plus 1. Well, that plus 1 isn't really going to do anything when you're getting very, very small. And so we have -infinity over -infinity. So this is another indeterminate form. So I can use the same reasoning I did over here and multiply this function by that fancy 1 over x. And when I do that, so really we're going to look at then the limit as x is approaching -infinity of, when we multiply by that 1 over x, we got this. We got 2 all over 1 plus 1 over x. And so when we plug in -infinity, we have 2 all over 1 plus 1 over -infinity. but 1 over negative infinity, that piece goes to 0. So we really have 2 over 1, which is just 2. So limit as x is going to negative infinity is equal to 2. So here on our graph, as x is approaching negative infinity, we're going to hug this horizontal asymptote. So we used information about vertical asymptotes, horizontal asymptotes, looking at limits as x approaching infinity and negative infinity, looking at limit as x is approaching a vertical asymptote on the left and the right to see which way it was going. And so let's look at a couple of other problems. And let's use that trick that I was just telling you about when we're looking at the limit as x is going to infinity or negative infinity. So I'm going to move this up. I'll make this big so I like the thick pen. I don't like that skinny. So if we have the limit, we're first going to look at f of x. F of x is going to equal about 9x to the 4th plus x all over 2x to the 4th plus 5x squared minus x plus 6. Okay, so find the limit of each of the rational functions, a as x goes to infinity and b as x is going to negative infinity. So if I go in here and I'm looking at the limit as x is going to infinity of this function, so 9x to the 4th plus x in the numerator, all over this 2x to the 4th again, plus 5x squared minus x plus 6 in the denominator, I'm going to get 9 times infinity to the 4th plus infinity, which is infinity, all over this 2 times infinity to the 4th plus 5 times infinity squared minus infinity plus 6 is still infinity. And so this gives me an indeterminate form. And so we need to manipulate this to help us figure out what that limit is. If it does have a limit going to some horizontal line L, or if it's going to infinity or negative infinity. So we're going to manipulate this by multiplying. Looking at this variable, I have x to the 4th. That's the term with the highest power. And so we're going to multiply this by a fancy one, which I like to call it. And we do that a lot to help us manipulate things. So I'm going to multiply both the numerator and denominator by 1 over x to the 4th. So if I distribute this to each term, let's just simplify. Let me know if you have questions on how I'm doing this, but I'm going to just do it. So limit as x goes to infinity. Well, if we have 9x to the 4th all divided by an x to the 4th, those x4s cancel, leaving us with 9 there. Plus, and if I distribute that 1 over x to the 4th times x, well, x over x to the 4th. That simplifies down where I have an x cubed in the denominator. All over. So now we have to distribute this 1 over x to the 4th to each term in the denominator. And so that would leave us, for the first term, we would have 2x to the 4th all over x to the 4th. So x to the 4th would cancel, leaving you with just 2. Plus 5x squared over an x to the 4th. So it doesn't all cancel, but we have a 5x squared in the numerator, and that x squared will simplify and cancel in the numerator and goes into the x to 4th down here, x squared times. So we have 5 over x squared there, minus x over x to the 4th is 1 over x cubed, plus 6 over x to the 4th, nothing cancels. And so now when we go in there and we plug in infinity wherever we see an x, we know that if we have 1 over infinity or a constant over infinity, that piece is going to go to 0. And so when we go in and we plug in infinity, we over this 1 over infinity cubed, that piece goes to 0. This 5 over infinity squared, that piece is going to go to 0. Negative 1 over x cubed goes to 0, and 6 over x to the 4th goes to 0. So we're basically left with, as x is going to infinity, this is equal to 9 plus 0, which is just 9, all over 2 plus 0 plus 0 plus 0, which is just 2. So as x is going to infinity, this has a horizontal asymptote at 4.5. Horizontal asymptote at y equals 9/2. 1/2. So that was part A. So same sort of reasoning as we go to negative infinity. So same function, limit as x is going to negative infinity. We have this, and I can have the same reasoning. I could multiply all of that through by 1 over x to the 4th. And when I do that, I have this 9 plus 1 over x cubed. I'm just using the work I did above, so I don't have to redo it. 2 plus 5 over x squared minus 1 over x cubed plus 6 over x to the 4th. So 1 over something that's blowing up, the absolute value that's blowing up, I'm just going to say it that way, that's going to go to 0. All these pieces again go to 0. And again, I can see I have a horizontal asymptote at 9/2. So as x is going to negative infinity, the graph is getting closer and closer to 4.5.
I had a question. So at the top, you multiplied by 1 over x to the 4th.
Right.
And on the previous one, you did 1 over x. Is it always a good idea to multiply by the biggest power in the equation?
Yeah, so look at the term that has, and so the term that has a variable raised to the highest power, and that's what you're gonna usually multiply 1 over that, both to the numerator and denominator.
Gotcha. Is there any other kind of modification that you would ever do for these types of equations, or is it just that's the best idea?
If they're polynomial in the numerator, polynomial in the denominator, that's how we're going to go about it, but it's not always a polynomial. So we're going to look at a case right now. So good lead in when you don't have it look like this, and I'll give you the tricks on how to simplify when it is in an indeterminate form of infinity over infinity. So for instance, and this actually kind of tells you. So let's look at the limit. As x is approaching infinity, let's say 2 plus the square root of x all over 2 minus the square root of x. So it actually says divide numerator and denominator by the highest power of x in the denominator and proceed from there. So they say the highest power in the denominator, and I don't remember that being in the case. I always remember just looking at the highest power of a term in either the numerator or denominator. But in this case, if we did what they said, well, they both have the same power. Remember with rational expressions, not rational, radical. So if I have the square root of a, remember this could be rewritten as a raised to the 1/2 power. So just kind of recall these things. If you had the nth root of a raised to some power m, we can rewrite that with a rational exponent, and that is a raised to the m divided by n power. And so I can rewrite this limit here as x goes to infinity of 2 plus x raised to the 1/2 power all over 2 minus x raised to the 1/2 power. So right now when I plug in infinity, this is going to give me infinity over infinity. Let me just do it up here. Infinity over infinity, which is the indeterminate form. And so if we use the fact, if we multiply again by the variable raised to the highest power, which is x to the 1/2, actually 1 over that. We're going to divide every term in the numerator by x to the 1/2 and every term in the denominator by x to the 1/2. So we get the limit of 2 all over x to the 1/2 because nothing cancels there. Plus x to the 1/2 all divided by x to the 1/2, which is 1. And this is 2 all over x to the 1/2 in the denominator minus, well, the x to the 1/2 cancel, leaving you with just minus 1. And so now when we plug in infinity, 1 over infinity, that's going to go to 0. In this case, 2 over infinity, square root of that still goes to 0. So we're left with 1 over negative 1, which is negative 1. So that's telling me that I have a horizontal asymptote. The end behavior of my graph as x is going to infinity is negative 1. One more. Limit as x is approaching negative infinity. This time we have 4 minus 3x cubed. That's in the numerator. And in the denominator, we have the square root of x to the 6 plus 9. Okay, so if we plug in negative infinity, I notice that I'm going to get in the top, I'm going to have some negative infinity cubed is negative times this negative out front. So I can do some reasoning that the top is going to actually go to positive infinity. The bottom, when I plug in negative numbers, I raise it to the 6th power. That's going to be positive. Square root of a positive is positive, plus 9 is also positive infinity. So again, I have this indeterminate form and I need to start manipulating this so that I can get it to work. I also notice that I can actually simplify in this denominator that x to the 6, that square root of x to the 6 actually reduces down to x cubed. So let's just rewrite it like that. So I have 4 minus 3x cubed all over x cubed plus 9. And now if I multiply by 1 over the variable to the highest power, so in this case, 1 over x cubed, multiply that both to the numerator and denominator. So when we distribute, we get the limit as x is going to negative infinity. 4 times 1 over x cubed, nothing cancels. We're just going to write it as 4 over x cubed. Minus, so 3x cubed all over x cubed. X cubes cancel, leaving you with 3. And then all over, distributing 1 over x cubed to the x cubed here. X cubes cancel, leaving you with 1, plus 9 times 1 over x cubed, so 9 over x cubed. So constant over x, as x goes to positive or negative infinity, always goes to 0. And so this is going to give us negative 3 over 1, or negative 3. Okay, so let's look at just a couple, let's look at one that has a vertical asymptote. So as limit as x is going to some value a, where we have a vertical asymptote, and see what we get. So if we had the limit as x is approaching 0 of negative 1 all over x squared all over x, and that x squared is all times x plus 1 in the denominator. So notice if we plug in 0, it's undefined there. X can't be 0. And so we need to look at what's going on the left-hand side and what's going on the right-hand side. And so let's look at the limit as x is approaching 0 on the left-hand side. So this negative 1 all over x squared, x plus 1. Okay, so if we're plugging in numbers where x is approaching 0 on the left, I'm plugging in numbers here where x are less than 0. Close to 0, but less than 0. So when I do that, I get negative 1 in my numerator. That doesn't affect my numerator. And so I get negative 1 up here, all over. So if I'm plugging in a negative number and squaring it, and then I'm going to have this negative number, which is really close to 0. So it's not going to be bigger than negative 1. So negative number smaller than 1, and adding that, that's positive. So I just want to see what kind of number I'm getting back. So I get a negative number in the numerator all over a negative squared is positive times a positive is positive. So this tells me that as x is going to 0 on the left-hand side, I'm going to go to negative infinity. It's just shooting down somehow. And then I want to see, is this going to be shooting down as x is going to 0 on the right-hand side, or is this will be shooting upwards? And so let's look at the limit as x is approaching 0 on the right. So negative 1 all over x squared all times x plus 1. So this is going to give me, so if I plug in a number on the right of x equals 0, those are values where x is bigger than 0. So that means I'm plugging in a positive number. So that doesn't affect my negative in the numerator. All over any number squared is always positive. And a positive number plus 1 is always going to be positive. And so this is negative over positive, which I know is negative. So as x is going to get closer and closer to 0 on the right, this will be shooting downwards and going to negative infinity. So you just have to kind of do some reasoning on the left and the right of your vertical asymptote and think about the numbers that you're plugging in. And are you going to get back a positive number or a negative number back? And that will tell us is it shooting off to positive or negative infinity. Okay, so we're almost done with this section. I'm going to get into a little bit with trig functions tomorrow, but we'll be finishing off chapter 2 tomorrow. And I might have you guys be working on an in-class exercise if we have time in class. So you guys have get a chance to work on some problems. But that is it for the lecture today. And so let me just stop the video, and then I have office hours if you guys have questions.